all of them, but they are, I will first talk about the size. I have to click. Right. All right. Okay. If I would like, shows all of the 5 different chromatography. This is what we talked about last week. So today, mainly on ion exchange. So if you look at the ion exchange, it is very straightforward. The column will have ion exchange capacity. So mainly it is for separations of anions and cations. So I will extend the mechanism later. Another one is affinity. So if you look at affinities, the definitions is separations of chemicals based on their interactions. Yeah. So usually we talk about biological sample. So like protein, enzyme, something like that. If you look at the picture here, it is very specific. Yeah. That means like, for example, enzyme, enzyme is very specific only for certain substrate. So it can only separate, or it can only hold, like retain certain specific compounds like this. Yeah, another one we call size exclusion. So this size exclusion includes gel filtration and gel permeation. Yeah. So I think last week we talked about, sorry, I have a chat message. All the recordings of, you can, okay, thank you. All right, so I think last week I showed this graph also. Like, okay, I will first talk about size exclusion. So as I say here, size exclusion will include gel filtration and gel permeation. So if you look at here, if I want to ask you one question, yeah. Sorry, my slide doesn't. Okay. What is the main difference between gel filtration and gel permeation? Yeah? Anybody can guess? If you look at here, the question here is water soluble. If it's yes, then we use gel filtration. Yeah? If it's no, we use the gel permeation. Yeah? So can you guess what is the main difference between this GFC and GPC? Just in case you know. Anybody want to guess? Like in chromatography, the main thing is the column. Another main thing is the mobile phase. Yeah. So if you look at here, water soluble, so it must have to be related to the liquid. Yeah. So the main difference is actually, okay, the main difference is actually the mobile phase. So in gel filtration, the mobile phase we use is an aqueous solution. For the gel permeation, the mobile phase we use is an organic solvent. And as you can guess, like for the water solution, we are able to separate proteins and water-soluble materials. And for another one, this one, we are able to separate polymers. Most of the polymers do not dissolve in water because they are actually like lipid-based. So they will dissolve in organic soluble materials. So usually, when we talk about gel permeation or gel filtration, the most common term we use is size exclusion. Yeah? So with the word size exclusion, meaning that, for example, these are the packing materials. Yeah. So the packing materials will have a lot of pores. We call it mesopores. Yeah? So the mesopores on the surface of the column will have something like this. Towards the center, the pore will be like smaller. And of course, the the entrance will be bigger. Yeah. So this is something usually when you make mesopores or when you make color materials, naturally they will become like this. Yeah. So the size exclusion is, for example, maybe you can guess already, the big size will go faster because they cannot go longer. Yeah. So I have made a simple animations. For example, you can see the small one will go through all the small holes. So by the time they come out, the big one will come out first, and then the medium size will come out in the middle, and then the small one will come out last, because the small one will go through all the small holes and their retention time is much longer. Yeah. So, and well, this one is showing the flow of the eluent. So if you imagine like a lever, the meter is always faster. Yeah. So meaning that the bigger one will also have the effect of this. We call it the flow profile, like this. So beside the pores, this flow of the liquid also will give an effect to the separations. So I have another maybe better one from the internet. So this is from one of the company who produce the porous materials like this. So if you enlarge this part, you will see it's like a lot of holes, like we call it, I don't know, it's like a web, you know, like a spider web. So whatever they can stuck in the hole will have a longer retention time. So if you look at, this is what we call the mesopore. The mesopore will have much smaller size. The through pores is about like 1 micrometer. The mesopore usually is about 20 nanopore, so nanometer. So if you look at here, it's the same here. Yeah. So once when we inject the sample here, for example, when we inject the sample, this is T0. So when we the longer we do the experiment, then we will have a much low molecular weight sample will come out. It's just like what is happening here. So in other words, not only having different sizes, but somehow when we also can design the shape, and of course, when the size is different, the weight is also different. Yeah? And we have did XCC before actually, because we want to separate nanoparticles. Maybe you know there are many nanoparticles being used in the market as a synthetic nanoparticles and also the natural nanoparticles. Natural nanoparticles is something like a virus, and then or something like when you have like you know, Japan and Indonesia, it's quite similar. It's a earthquake country. Yeah? So when there's a earthquake or when there's a volcano eruption, you can see that's a lot of particles coming to the air, and also like a PM 2.5. So PM 2.5 is also particles, but they are micro size. Actually, they are even lower nanoparticles. Sometimes for the woman, when we use the cosmetic, we used the nanoparticle. For example, silver nanoparticles will be in the like a sunscreen. Yeah, when you want to put like a sunscreen to block the sun, usually the silver nanoparticles will be used in cosmetic products. So therefore, in Japan, at one time, it was a boom to separate nanoparticles. So we try to use different columns to separate nanoparticles. At the beginning, we try to separate silica colloid with 5 nanometer, 26 nanometer, and 78 nanometers. So this is one of the chromatogram we usually get from the experiment. I want to explain about this chromatogram. Maybe you already know for those who have done some simulation. Yeah. So this is the packing materials that we pack in the column. It's from a company called Sepex. So it's called Sepex SEC size exclusion column with 1000 here. So 1000, it stands for the meaning, the product meaning for the company. When we try to look at the you can, if you want to know more details of the packing materials, you can Google Sepex XRT SEC 1000. Then you will know the pore size, you will know the pore volume, you will know the Mesopore volume also. So here we pack 0.53. It's a capillary with 30 centimeter. So when we inject the sample, T0 here, so the first page, we call it the exclusion limit. Yeah, exclusion limit means the sample will not have any retention, just pass by the column without anything. So it's called exclusion limit. And then I also use another sample, which is the toluene. Toluene is a very small molecule, and this molecule will go through all the small holes on the column. So the toluene peaks will be called the permeation limit. Yeah? So the between the exclusion limit and the permeation limit, we call it separation window of the SEC. So meaning that the biggest size will come out here, and the smaller size will come out with toluene. So in between, only the size between toluene and the biggest silica will be separated inside this range. There will be nothing come out here. There will be nothing before here also. That is why we call it separation window of size exclusion. So usually when you want to buy a column, you have to see the separation window. Yeah, the bigger the separation window it is, the column have more capacity. Yeah, so sometimes sometimes when you want to buy an XEC column, some company they offer very cheap column. Yeah, then at the time you have to compare the size of the material. Sometimes it is not so good. Yeah, same size, 30 centimeter, but if the inside is not good, then that means your separation window is very small. Yeah? So it's useless. But anyway, it was difficult to separate the 5, 26, and 78. As you can see here, when I used methanol as the eluent, because I want to have a very low viscosity than water to do the separation, but for those who know, it's overlapping actually, so the separation was not good. So after that, I tried to change the eluent. From methanol, we changed to water. You can see the 5 nanometer, it's already separated from the 78 and 26. Yeah, but between the 78 and 26, it is still very small. You can look at here, the separation window for the silica colloids is actually quite small. So we also try another method. It is not the same as SEC, size exclusion, but it used the same phenomena. Today, if you have time, maybe you can go back and Google. We call it HDC. HDC stands for Hydrodynamic Chromatography. So hydrodynamic chromatography means that, for example, this is the packing materials without any mesopores, for example. Yeah. So for example, this is a non-porous materials, and you have, for example, the size is about 1.9 or like about 2 microns. No matter how good you pack your column, there will be still some holes like this, right? Okay, we use these small holes to separate. Yeah. So whatever that go inside here will have, for example, when we calculate it, the size is about 45 nanometer. the biggest here, for example, the size we put here is 78. So meaning that, for example, if we have like a porous, and we also use the hydrodynamic separation interactions. So you can have double interaction. Right? Double interactions means you can have the size of the mesopore, and you also have the size of the like a hydrodynamic, like we use this kind of small, we call it like a flow between the particles. Yeah. So this is just an image, you know. So when we combine both, you can see we are able to separate them like this. So in this case, this one stands for the size of the particles, the packing particles. So this one stands for the size of the bigger one. So compared to the 3 microns, when we use a smaller one, like a 2 microns, you can compare the source separation. This is a bit better than this one. Yeah. So this is just some example that you cannot find in the textbook. So other things, if you want to know, you can actually read from the textbook. But for size exclusion, just remember, you know, like this question, why is it so important we measure the molecular weight? Yeah. Any idea? Why is it so important? Yeah. Sorry, I have somebody knock on my door. Sorry, I just put something on my door. Okay, all right. Anybody want to try? Why is it so important to measure the molecular weight distribution? Well, actually, usually, you know, when we, it's the much easier way to measure the size is actually light scattering method. Yeah. So light scattering is like you just put something, and then when, for example, you have a liquid, yeah, you just use like a light, whatever light, then you can see when the different particles, they will scatter different light. Yeah? So when you calculate the angle, you can actually measure the size of the particles. Yeah. So this is usual when you want to know how much particle size is inside one solution. Yeah. But another method is called the osmotic pressure method, and the other one is called viscosity method. This one is a bit similar, yeah. So we use water with different viscosity. So, but in this case, it takes a long time, and then the separation is not good if you want to do a separation, yeah. So normally, you know, there are so many polymers, synthetic polymers in the market. So the polymers does not consist just one weight. Yeah, it's like a collections of different weights. Even synthetic polymer, when you want to buy something, when in the bottle, yeah, it's written average size like this, how many molecular weight, yeah. But actually, it has so many different kind of sizes. So when we use SEC, we can see the distribution of their molecular weights, and then we can, from there, we can see the different properties, which is usually come together with the weight and also with their size. So anyway, just remember this one. The important thing that we need to know is the polymer or whatever, they don't have one single size. There is like a collections of different sizes. So we have to determine their molecular weight in order to test their different properties. Yeah. So this is one of the important reason why we want to use SCC. Another thing, well, most of the thing beside polymer, it's protein separations. So protein, when you have different kind of proteins, but most of the time, the protein will have hydrophobic interaction. Yeah. So compared to size exclusion, it is better or it is easier now to separate proteins with the reverse phase. So you can also use SEC for big protein, yeah. But most of the time we are interested in smaller proteins. So most of the time we just use reverse phase because we can use the hydrophobic interactions. Okay, so I will try to, it's maybe a bit fast, but I will go to affinity. Maybe at the end, you can ask questions at the end if you want. Anyway, the next one, I will go to affinity first because maybe it is easier to understand after the size exclusion. So affinities are usually, usually involve biological samples. Yeah. So I have something on the screen. Do you see some like something like this here? Maybe you don't see it on the screen.
Yes. I see it, Prof. Maybe someone using. Yeah.
Sorry.
Wait.
But it doesn't matter. I don't care. I can continue.
I think you can erase it.
I can erase it.
Yeah, you can erase it.
Or is it because of me, Kana? Oh, do I there? Let me try. Okay. Sorry, just don't know. So when I share the thing, it's
okay. I think it's clear.
Okay. Now it's deleted. Okay, thank you. All right, arigato. Okay, hi. Anyway, affinity, it's separation based on specific interactions, like I have mentioned before. So usually it's immobilized. Yeah? Immobilized means something we fix on the column, like a ligand and the binding partners. For examples, antibody and the antigen, enzyme and the substrate, and also the something like another enzyme with the inhibitors interactions. So it's very specific. Yeah? For example, enzyme, and for example, if we if you hold on. In my lab, I did before like trypsin. Yeah. So trypsin is like an enzyme. So we immobilize trypsin on the like a silica surface, and then we were separating some proteins like the any proteins. So we try to do the digestion. Yeah? So it's like online digestion. We use the column as the microreactor. So yeah, I published a paper a very long time ago, maybe in 2006. So it's about a trypsin column. So at the time also, only protein that can be digested by trypsin. And then after the digestion, we'll have different peptides. So we will, sorry. So we have different peptides, and then we are able to do different separations that time. And then the important thing of the purifications, it's about specific interactions. Usually, it's important when we want to do purification. Yeah. So Yes, especially for purifications. So this slide is, yeah, I'm just having a short questions. So why do we use affinity chromatography? Yeah? So, well, in my previous slide, it's having very high selectivity and also resolutions and capacity. Yeah? But well, the capacity actually depends on how good your reaction is. Yeah. So if your immobilization is not so good, then it will affect your resolution. So usually you don't do yourself because the reaction is not so easy. So usually if you want something, you will buy from a company. It's easier to buy because they have already developed many column like this. Usually it's more very specific. Yeah. For example, if you say you want to separate exosome or whatever, then they will give you a different catalogs. Then you can try to see which one you want to buy. Yeah? So most of the time it's about protein purifications, and it has the advantage like without compromising the functional of the properties when after the purification. Then as a result, we can actually save some time, and also we can achieve um, something that we cannot achieve with another column. So for example, okay. Anyway, I will, this is, for example, there's one target protein like this here. So usually we will design the particles that have different affinity or different binding size, So only a certain proteins or only a certain compounds that have the interactions will have that will fix the size. For example, when this column have triangle size like this, for example, triangle is just the shape of the binding site. So for example, you have a different proteins with different sizes or different morphology or different molecular or different structure like this. Only the one with the triangle like this can fix exactly to the column, and the rest will not have any interaction. Yeah. So only the one that fix exactly the hold or the binding site that will retain. So and other compounds or mixture will be come out. Yeah. So after that, we will use a buffer, a stronger buffer to wash the column. And after washing, usually we will do, usually we have to use a strong salt because the salt will wash inside the holes, and whatever we need, we can wash back. And then we can regenerate the columns, and then we can get whatever we want. So this is from one of the company that produce column for affinity chromatography. I think if you Google on the internet, you can get some something like this. At the end of the lectures, if there's a time, I will share some of my results that I got before with the trypsin immobilizations. I don't know if you're interested to know how we immobilize trypsin. Maybe it is not so interesting. It's, yeah. But anyway, yeah, it is very specific. Yeah. So the mechanism, it's already fixed. It's just only that certain ligand can have a match with the column, can be retained, and can be selectively separated. Yeah. So when we use affinity chromatography, usually it is important for the development of drugs, because most of the drugs, it's actually quite in small amount, and they are very expensive. So to do the purifications of drugs takes a long time. Yeah? So usually after size exclusion, some people will also use affinity to have a more pure compounds of the drugs. So you don't use affinity from the beginning, yeah, because if you use from the beginning, then the column will not be so good to the column. So usually you have to use another column, like a gut column, to do some screening first. Then what like a washing method, yeah. So after you use some other columns, then when you have a half pure compounds, then you will use affinity column to have a higher purity compounds. So yeah, so anyway, if you have any question, you can ask later. But like I said before, it is very specific. Yeah, like only this binding like between the antibody and the antigen and enzyme and the substrate, and also between enzyme and inhibitors. Yeah. So from the beginning, when you buy the column, it's already very specific. Yeah. So sometimes you can select based on the functional groups. Sometimes you can select based on the like a binding site, like for example, how many glucose you can bind. Yeah? So if you just want to have 3 glucose, then you can have a column that can bind only 3 glucose, yeah? Something like that. So it is quite convenient sometimes if you have a good column like this. But you can also make yourself just very difficult to maintain a high capacity. Yeah? So usually it's easier to buy because it saves time. Right. Another one that we will talk today is ion chromatography. Like I say in the beginning, it is very straightforward. It is based on the binding of fixed charges on the support. So if you want to separate ions, then your column will have anion exchange site so that you can have a different charge, will have different interactions. Yeah. So this ion exchange, I think at the beginning when I talk about the history of chromatography, yeah, so ion exchange chromatography actually starts from 1949. The mechanism, yeah, start from 1949, but ion chromatography as a system, it was sold in 1975. So 1969 is the first HPLC. Yeah? So after that, they changed the column with some different exchangers. And then they have ion chromatography in the market for sale. I mean, commercial, the first commercial ion chromatography, it's 1975. So at the time, the detector they use is a conductivity detector. Yeah. Conductivity means the detector can detect based on the charge of the samples. So depending on your eluent, you can choose a positive charge or you can even choose negative charge. So the detector will measure the difference between the sample and the eluent. So anyway, for the column, basically there are many types of columns, but the functional groups is actually quite similar. It's quite fixed. Yeah? So for cation exchangers, usually there are 2 types. The strong one, we use the sulfonium group like this, and the weak cations is carboxylic acid like this. So when the proton is gone here, so you can see here, there will be a negative charge. So this sulfonium group and the carboxyl group will be used for cation exchange. And for anions, most of the time is amine based. So the strong anion exchanger is quaternary amines. And the weak one is like primary, secondary, or tertiary. They are relatively weakly basic for the anion exchangers. So well, actually, the functional group is almost the same, yeah. Just that the molecule they used for the reaction when they make the column may be different. Yeah, most of the time it's aminopropyl. So propyl means there will be three C3, like the C3, and then with the amino group at the end of the column. So that's what we call an aminopropyl. Yeah. So this is very traditional, meaning that your column will have ion exchange capacity, and then you can separate the anions or the cations, whatever you like. But sometimes when people who has a Hplc column, you actually do not need to buy an extra column just to separate something you just want to test. Yeah. For example, if you have time, maybe you can Google ion partition chromatography. So ion partition chromatography means that we will coat something on the surface of the packing materials, and then the coating surface here will attract the eluent cations like this. So, and then the attracted cations from the eluent will become the ion exchange site. So, for example, PEG. PEG is a like a amphophilic, yeah. So actually, our group started this ion partition chromatography some like 15 years ago. So it happens that actually we wanted to use PEG to separate nanoparticles, yeah, but we could not make it. And at the time, there's one PhD student, when she mixed like just 5% PEG with the molecular weight 20,000 in just water, yeah, you can see it's a homogeneous phase. But when you mix under 1 molar of like a sodium sulfate here like this, the salt, any salt with 1 molar, you can see the water phase become 2 phases like this. So the PEG will be here, and then the salt will be here. And there is a surface, like a hydrophobic surface, happen like this here. So meaning that on the surface of the column, actually the layer of the column can be different if we have a different thickness of the PEG. Remember I said before, when we have this absorption and like last week when we talk about the partition chromatography. So, you know, the layer of eluent will form a different layer, like an eluent layer on the surface of the statinated phase. And here we'll have a different partition will be happening. Yeah? So it's quite similar, like when you use a liquid-liquid partition. Yeah? So what is convenient about this is we can modify the separation capacity, or the separation, we call it selectivity, by choosing different eluent. Yeah? So this is become the like a principal separation for reverse phase and normal phase. Yeah. So another type of IC, we call it, it is similar to what we call like a Illumine-Induced ion exchange chromatography. So because in any Hplc system, usually you will have a C18 column. Yeah? So if you buy a new system, if you just want to separate something, for example, you just want to see some ions, just want to see one sample, you don't need to buy a new column. Yeah. So at the time, you can use eluent additive. You mix something in the eluent, and that something will be absorbed on the C18 or the C30 or whatever. Usually it's C18 under hydrophobic interactions. And then you can have the separations. For example, this one is a crown ether. So crown ether can have different sizes, yeah, like crown 18 or crown 16. So the size of the crown ether here will depends what kind of ions you can extract or you can separate, yeah. So crown 18 is actually hydrophobic. So if you add crown ether a certain amount, like 5% or whatever in the eluent, the crown ether will form a layer on your C18 column. Yeah? So when there's a C18 column with a layer of crown ether, and if you use the eluent that contains like a potassium, like the kalium plus, kalium and the C18 comment and the crown 18 have exactly the good same size. Not exactly, it's very good for the kalium size. So the eluent ions will be trapped on the crown ether. And then here you can have the ion exchange site. Yeah? So this is what we call the Illumine-Induced ion exchange chromatography. So in this case, after you test your sample, you can use a salt to wash away the crown ether, yeah? And then you can regenerate or reuse your column as a C18 reverse phase column without any problem. So this is very convenient when you want to use a typical Hplc system to separate anions. So recently, well, in ion chromatography, there are many different systems actually. So recently, some people, they want to separate anions and cations at the same time. So usually, some people will try to make what we call a zeta ionic column. Yeah. So originally, it was used to separate anions and cations. But right now, because of helix, helix is another kind of partition. I think we discussed before helix. And helix can be actually very useful when we use a zeta ionic system like this. So anyway, if you have time, you can Google, hydrophilic interaction chromatography helix. I think we discussed a bit last week. But anyway, if you want to know more details, recently, people will use zeta ion as the selector for the helix column, yeah, which is better than the usual polar phase. Polar phase is polar, with we just used the distribution of the electron. Yeah? But in helix, its charges, we can have the electrostatic interactions. And at the same time, we also can have hydrophilic interactions. Yeah? So it will be more convenient. We'll have better separations. Okay, so well, there are many systems on the market when you want to buy IC ion chromatography system. Most of the time, you have to buy different system, yeah, like anion, then anion exchange column, cation, then cation exchange column. But for here in our lab, we sometimes right now we don't do this because it's already old-fashioned. But before that, if you use a switching valve like this, you can connect the anion exchange column and the cation exchange column like this, and then you can have the same system with different separations depending on what kind of compounds you want to separate. Yeah. So sometimes it's one system, like you can share the same palm, you can share the same detector, data processor, just use one valve, you can have two systems. Yeah? So sometimes it's also very convenient if you can have a valve like this. So yeah, before that it was popular, like how to do the switching, the timing of the sample injection. It's not so difficult, but you need some technique to do the switching. Once the switching is not correct, sometimes your sample will go to the drain, not going to the column. So, well, sometimes it's a bit tricky, but if you are familiar with the system, maybe you can know something like this. But anyway, and another, oh, anyway, this one is for the simultaneous separations of anions and cations. Another system that I would like to introduce is what we call the suppressed ion chromatography. So this is the first commercial system of ion chromatography introduced in the market. If you look at the system, compared to a usual single column system, single column means only one separation column. You can see there is a suppressor here, yeah, before the detector. And then there is a guard column here. So guard column is just to make sure there's no other, like usually it's like a hydrophobic or even hydrophilic, depending on what kind of mixture of samples you can have. So guard column is like a filter, yeah, to filter something with a bigger molecular size. And then so that your ion samples will go to the column. Suppressor is also like another column, and before the detector. Yeah. Anybody know what is why we have to use a suppressor here? We call a suppressed ion chromatography. Maybe it's difficult for you to know. Yeah. Well, the reason is to increase the detection sensitivity. Yeah. Like, for example, when we use the conductivity, sometimes some eluent, the conductivity is very high. For example, like this. So this is the actual chromatogram we got when we used a suppressor or without a suppressor. Yeah? So when this is the baseline, when we do without a suppressor column. Yeah? So, but with the suppressor here, the background of the eluent will be reduced. So whatever here, if you enlarge here, you can see there are actually some peaks here. So if you do not use a suppressor, meaning that the background will be like this. And whatever come out in the lower area, you cannot see at all. Yeah. So this is happening when you need a certain eluent to separate something like this, but the background of the eluent is very high. So that's why we use a suppressor to suppress the background first like this. And then at the low background noise, we can do the separation like this. And then when we finish, we just turn off and the suppressor will go up again. Yeah. So this is just one example. We used the system. So I will explain. The system is a THK gel ion exchange column. So we pack in the capillary. Yeah? So we use contactless conductivity. So, well, contactless is another different types of detector. It's for capillary. It's just the meaning is just doesn't go through to the detector. It's, if you Google, you can have a more easier understanding definitions. So anyway, this is one example of the maybe it's okay. I have a phone call, but I will ignore. Anyway, this is like, for example, one of the separations of 1, 2, 3, 4, 5, 6 anions when we use a suppress system. So usually after the separations of something in ion chromatography, we can, if you want to do the real analysis, we have to use calibration, yeah, like calibration like this. So when we increase the sample concentration with 0.01, 0.05, then 1, 5, you need at least 5 points to have different calibration curves. So when you have different calibration curves, and then you can determine your detection limit of your column, like the this is what we call the limit of detections. Under PPB, you can see with a suppressed system, your limit of detection can be very low to PPB level. Yeah? And then the linearity here, as long as it is more than 0.99 and above, it is okay. And then they will be like a time like this. This is the retention time of the samples. So after you have the calibration, you also usually we will have to test whether the column is repeatable or not. Repeatable means you do 6 times, the same sample 6 times, and then you calculate the relative standard deviations. So we call it RSD. So if you have all the data for retention time, peak areas, and peak height, then you can calculate the average, and then you can divide the standard deviation with the average. You can have the relative standard deviations with some percentage. So as long as your RSD is less than 5%, that means your column is repeatable. It's considered good column. Yeah. So so when your column is good, you can try to analyze some sample in the real sample. So ion chromatography usually is used for environmental analysis. Yeah? For example, here you can determine some like nitrate. It's quite a popular sample, yeah, because when there's when it is near to the agriculture area, you can see most of the it's contain some nitrate into the water or whatever. And in Japan, the tap water in Japan is regulated. Nitrate and nitrate, I mean the NO3 minus and NO2 minus have to be less than 10 ppm. Yeah? So, well, 10 ppm, it's the regulation doesn't apply to other countries, but I think maybe Indonesia, it's higher regulation. I don't know, but in Japan, the nitrogen, I mean the nitrate and nitrite, it's have to be less than 10 ppm. So usually we also like test some tap water, but I have some graduates who are working in the we call it the water the tap water system division of the government. So they use ion chromatography to regulate the quality of the tap water. Yeah? So beside sodium, there are so many other things to test, like other chemicals. Yeah, so it's have to be safe to drinks. So liver water, usually you can have some like socks like this because acid rain. So sometimes acid rain, or even in a pond or whatever. So I have some project with the local government before, but the project is already over. The project started 20 years ago when I was a student. So it's like a national project to test the acid rain, effect of acid rain on a local pond. There's a local pond in Gifu area. We call it Ijira pond. The pH is so low, yeah, like 4 something. Yeah. So it is affected by the acid rain. So the government contract different locations to see the effect of the pond and also the river by monitoring the pH and the ions inside the natural waters. Not so much. It's just once a week, every Monday. We go sampling every Monday, and then Tuesday we will do the analysis. Yeah. So once a week, we will regular the amount of anions, and then we can calculate why the pH is so low. Yeah. So this is one example. Some ions you can find in the tap water, like fluoride, and well, depends on the area, and sometimes it depends on how you do your water treatment system. Yeah, chlorine, we use chlorine a lot. And then, anyway, sometimes if you look at the peaks, maybe look so big, yeah. But when we calculate, the value is just ppm, is less than ppm. Yeah. So for example, here is 0.068 ppm. So it's actually quite small, and you don't have to be really worried. Yeah? Well, for chlorine, even though it might seem high in the well water, is as long as you don't feel the smell is very bad, it's okay. Yeah? Because we used to kill the bacteria, so it doesn't really matter. If you feel it, the smell is okay, then you don't have to worry about chlorine. Yeah, yeah. Okay, 50, okay, for drinking. Yeah, then it's the same, yeah, 10 ppm. Yeah. So anyway, so then this is one example of what how we used ion chromatography for the monitoring of the quality of acid rain. So anyway, I have some times left, so maybe I will share something about oh. Anyway, while I open another file, anybody wants to ask something, you can ask now.
Oke, ada nih. Silakan ada nih. Please.
Hello, Professor. I want to ask
Yes.
something. Okay, wait. Maybe I will put it in the chat box.
Okay, Satria, right? Okay, bigger molecule has bigger result in peaks of yeah, usually bigger molecule we have a bigger detection. Yeah, yes. Usually we use depends on your detector. Yeah, so if the detector is light scattering, or usually we also use if the molecule you want to see contain UV, you can use UV. So most of the time beside the UV, the light scattering also affect. So usually you have a bigger peak. Yeah, usually. Yeah.
Okay, thank you.
Yeah.
So there's another question. Oh,
Yeah,
this
from
is
Adani.
from
Yeah.
Adani. About the separation mode of size exclusion, the smaller particle will go to the the inside of the component and will come out late. Will there be a few or smaller particle that's stuck inside? Yes, there will be something that's stuck inside. Yeah, yes, there will be. This is a very good question. Yes, this happened when we separate nanoparticles. Yeah, so at the beginning, we found out that the nanoparticles actually got stuck inside the column, yeah? And it doesn't come out no matter what eluent we use. So at the end, we have to wash everything with organic solvent to clean the column. Yeah? So that's why, because of that, we gave up the separations of nanoparticles. Yeah. But for other particles like micro size and above, yeah, usually there's no problem. Only you have a problem when there's a size lower than sub-micron, which is like a nanoparticles. Yeah. I hope this one will answer your question, Adani. Yeah, it's a good question.
Very good question.
Yeah. Artist D from Chemistry D. I have a question about ion exchange. Okay, previously I had read a journal that synthetic materials are usually used, and I may know more about this material. Yeah. So that in ion chromatography, the color materials all are synthetic. Because if you do not use synthetic materials, the size of your particles will be so many different sizes. Yeah. Yeah. So at the moment, yeah, it's only synthetic. Yeah. So, and I don't know, this is another slide I tried to use before. So like just now I mentioned about the contactless detector. So this is the contactless detector that we use. Yeah. So usually for for usual system, you don't need a contactless system. Yeah? Contactless, it means this is the sensor actually. I cannot bring my other sensor now, but if you look at here, this is one of my students' hand. So it's a he Anand is from Indonesia. Right now he is working as assistant professor in another university in Japan. So this is the capillary column we made. Yeah. So this one, actually, it is this contactless detector. Usually it is used for electrophoresis. Yeah. So, but we try to use this detector as a universal detector for ion chromatography. So we put because the size of the capillary is just fixed with our capillary system. So we can use our column on the sensor, and then we can use it for detection, yeah, which is quite convenient. Yeah. So in this case, sorry, got it? I want to show you the flow cell. Yeah. So the detection flow cell can be a non-conducting materials like a fused silica. So our column, we use a fused silica, and the peak mean the polyatomic ketone. So this is not so much because it is not so flexible. So compared to peak tube, you can use the Teflon tube, which is also plastic. It is a bit softer, but it is more expensive. So usually silica is also expensive, but because it's like a glass, it's stronger compared to Teflon. Yeah? So as long as the outside diameter is less than 400 microns, we can use. So the advantage of this contactless is it's very easy. Yeah, we just use our column as the detector. It's so convenient for capillary system, and then it's contamination free, and then you can avoid that volume. That volume means the volume between the detectors and the column. Yeah. So if you use a packed column, you have to add an extra connector to connect the column and the detector. Yeah. So if you use direct the column as a detector inside the detector, that means there's no depth volume and your peak shape will be very good. Yeah. So this is one of the good, I mean, like the advantage of using the contactless detector. Well, actually, it is not so common, yeah, because not many people will want to use it. Only people who are using capillary system will want to use this system. And okay, while I look for other possible example that I can share, what do you want to see? Or maybe there's one student say about the synthetic column. Yeah. Okay. Maybe I can show some slide how we make. Well, so there may. Oh, this one looks so. This is actually one system in my lab. Yeah? So, well, if you look at the usual Hplc system, you may see this one so messy, so many different things. It's because we buy the parts by ourselves and then we connect by ourselves. So like it is so messy. But this is the generator, and then this is the detector, this is the sample, this is suppressor. We use a suppressor, yeah? And this is a sample injector. So there are two valves. We use the two valve for two suppressor system. This is another system that because we want to use the suppressor at the same time when we want to use the detection. Yeah? Because usually if you connect the suppressor after the separation column, after some separation, the suppressor will be full, yeah? Because you have to suppress the background. So the suppressor will full with different suppressed ions, and you have to regenerate the column before you have to use again. Yeah. So we use this system is because we use two suppressor with two valve, so that when we switch one valve, we use one suppressor, the other suppressor we can regenerate. Yeah. So meaning that you can run all the time without waiting for the regeneration time. So this is one system that Anand was doing for his PhD project. So it was very long time ago anyway. So yeah. Another good thing is I said about the universal detector, because in liquid chromatography, the best detector, or we call the universal detector, we call it refractive index, which is cheaper. Another one is mass spectrometer, which is so expensive. So at the moment, these two universal detector is in the market, depending on your budget. But most of the time, people will have LC-mass, yeah? Because especially for the lab who are doing research in like metabolomics. I don't know if you know metabolomics. So it's like one of the omics, the youngest omics analysis in the market. So it is to separate and to analyze the metabolites. So the term we use is metabolomics. Yeah? So if you Google omics, or if you Google metabolomics, then you will know it is a new research area in analyzing metabolites in our system. Yeah? So most of the time we use LC-mass. So anyway, I will talk about the detector, the different detector, when we talk about our, I think we have an HPLC class just to talk about HPLC. So at the class, I will not talk about the separation mechanism. Yeah, I will talk about the system, like injector, detector, something like that, which is very important in the HPLC system. There are so many detectors in the detection. And depending on the detector, you have so many different kinds of sensitivity, selectivity, and there are so many different kinds of systems. So maybe I will share a bit about the result, or I'm still doing some collaboration with one of my graduates. Maybe later, Mora already give you the flyer of our webinar. So Dr. Rafi, he's the president, I think, of the Chemical Society of Indonesia now. I think maybe one of the youngest president. Yeah. So young, and he became the president of the. He was so shocked when he got selected. Yeah, I said, "Huh, you president?" He also got so shocked. Anyway, right now he is a current president, and then because of Corona, he was supposed to finish, but they extend 1 more year for him. Then I told Rafi, you are young, you should work harder and you should contribute more to Indonesia. And maybe for those who know Rafi, he is a very gentleman. He is a very nice guy. Anyway, I'm sure you will enjoy his talk. Yeah, his major is metabolomics actually. So especially for the analysis of jamu, maybe you know jamu. So Indonesians has one of the biggest jamu market in the world. Maybe after, I don't know, after India or after China or Brazil. Brazil also have a lot of different compounds right now. So anyway, maybe I can. So Ion Chromatography. Anyway, oh yeah, I was preparing something for the webinar about Ion Chromatography. Yeah? Maybe it's not complete, but I will just, I don't know what else I can share. How we make the column, the synthetic column. Yeah. So, well, actually the easiest one is to use polymer. Yeah? So polymer particles is easier to make. So sorry, just so no, I don't know what kind of things that I can share here, but so done. This one, sorry, this one is for chiral separation. Yeah? Maybe it's a different kind of separations. I will look for another one for the ion chromatography. Ion chromatography. And okay, I have another question. Is it okay for Susanti? My name is Susan. Food from chemistry. Chemistry. What caused our chromatogram to go out like a baseline drift of peak tailing? What caused it to happen, and how can we solve this? For the baseline drift, I think so done. I think last week when I explained one of the C30 columns, the background was drifting. So I'm not sure if you want to ask about this. Oh, gomenasai. Sorry, my computer stuck again. So, oh, okay, this one. Yeah, last week, I think maybe Susanti's question is about this baseline drift, yeah. So last week, the baseline drift like this happen, sometimes is caused by the eluent, yeah. So when the eluent, the viscosity change a bit in the system, it will cause a different pressure to the column. So when it causes different pressure to the system, it will cause a small drift of the baseline like this. Yeah. So this is, we call it the upper drift. Sometimes you have opposite, yeah, going down also. You can have a different shifting, either going up or going down. So usually shifting is caused by the pressure of the system. Yeah. So another question you asked about the tailing. Yes, tailing. Yeah, this is also we call it fronting. Yeah, tailing is maybe like this. Yeah, so fronting is before the peak, tailing is after the peaks. Yeah, and this one usually have to do with your column. Yes, so if your column sometimes it's being contaminated or something, you can solve the tailing by washing the column with a different eluent. Yeah? For example, this one is a hydrophobic column. So we use a buffer. For example, this is a gradient illusion using different buffer. Yeah? So in order to clean this column, usually I will use methanol. Yeah? So depending on the polarity of the column. So if you want to wash everything, because if the hydrophobic column, that means the hydrophobic compounds will be usually absorbed or like so strong they never want to come out. Yeah. So when you have more hydrophobic like this, compound like this, sometimes you will cause the tailing or the peak fronting. Yeah? So in this case, you have to wash your column to wash out the hydrophobic compounds. You have to use a strong solvent. Yeah? I hope this one will solve your answer, solve your questions. So while waiting, I'm still looking for a good slide to show for making the. Oh.
Well, Prof, I'm very curious about the suppressor. Yeah.
Okay.
What kind of material in the suppressor?
Usually the suppressor, it's also the same materials as the column, yeah? But the suppressor have to have a big capacity. Big capacity. So, okay, I will show this one. It's the one that Anand made for me. So, I'm not sure if you can see the slides here. So why do you stagnant maintain the background? So okay, maybe this one. Okay, so usually the suppressor will have a stronger capacity. It is also the same ion exchanger we used. So usually it's K-ions. Yeah? So we have to have something like a resin here. It will have a strong retention to the K-ions. So when you have OH or the, how to say, the conductivity, you can see there is a list of conductivity list. Yeah. So when usually we use this as the eluent. So and this sodium bicarbonate usually have a strong conductivity. So we will have to suppress first so that it will become a low conductivity like this. Yeah, with carbonic acid. Yeah, so which has a lower conductivity. So it's almost the same materials like a column. Just we need something with the higher capacity. Yeah, higher capacity. But you do not need to have a very usually the suppressor is not so cheap also. Yeah, so that's why. But when we use the suppress system, the sensitivity is very high, and usually when you buy ion chromatography, usually it will come with a suppressor system. Yeah? Right now, if you want to buy, yeah. But in the market now, you can also buy, we call it single column ion chromatography. Yeah? Single column means like only one column, but the technical term stands for non-suppressor system. Yeah? So in this case, you cannot use conductivity detector. You have to use like UV detector or other detector. Yeah. So most of the time, some ions will not have UV absorbance. So you cannot see the ions using the UV detector. So when you want to separate or when you want to detect ions, you have to use conductivity detector. Yeah? So actually there are many kind of system in the market, even using UV. If you change your eluent, you can actually modify your separations. Like usually the detector will detect the difference between the sample and the eluent. Yeah? So the lower the eluent, you can have the higher sample detectivity. Yeah? But for example, if your sample do not have a UV, but you only have a UV detector, so what do you do at the time? You can modify the eluent. Yeah? That means you can use a eluent with high UV detector, and then when your sample that do not have UV, you will come out as a negative peak. Yeah? So in this case, we call this indirect detection. Yeah? Indirect means usually it's not there, but we just change, modify the eluent and so that we can see the sample. So in this case, your peaks will come out as negative peak. Yeah, I have some example also. I will show you some example. This is also popular in ion chromatography. Yeah? So I have. Oh yeah, remember that I talked this one. So on. Yes. This one means indirect detections of okay. Remember I said about size exclusion. So for example, this is the example that we use to detect a polymer like ethylene glycol. Yeah. So ethylene glycol can have so many different types of molecular weight, but the thing is that ethylene glycol do not have a UV absorbance. Yeah. So you can see here, ethylene glycol will come out as a negative peak because we will have, we use something like sodium nitrate here, which have a high UV. So anyway, well, this one maybe is difficult to understand. I will pass. So anyway, for example here, so ethylene glycol will have negative peaks because there's no UV. And here we use a high
Prof,
background.
excuse me, maybe there is something error in your slide because this is
Oh.
clicking like clicking.
Oh,
I don't
really?
know. I don't know in others.
Oh, maybe it's like before, yeah. Sometimes when I open too many files, I remember last time it happens. Yeah.
Yeah. I guess so.
Yeah, I remember before. Today I used to so that. So, はい。はい。Oh gosh. あれ something is stuck with my PC. ごめんなさい。あれ why I cannot see my Zoom? Oh, okay. はい。I will share my. Okay. I hope now you can see my monitor. I'm sharing another. Okay. Anyway. So does it click now? I hope it's okay.
Yeah, excellent.
Okay. So this is an example when we separate polyethylene glycol with the molecular weight 200. Yeah, even though the molecular weight it's called 200, but when we separate them in like a reverse phase column like this, you can see there are so many different like a dimer, and this one is with the 4 molecular weight. This is the base of the ethylene glycol. Yeah? So the N will equivalent to the number here, N2. So we found out that if we separate PEG 200, we can have a distribution between 2, 4, 5, 6, 7, 8 different molecular weight of distribution. So in this case, because polyethylene glycol usually do not have high UV, so we used 5 millimolar of sodium nitrate, which have a high background, like 740 millivolt. Maybe you cannot understand what is this, but this is considered the background. So we increase the background UV, and then when the sample do not have a UV, it will come out as a negative peak. Yeah? So this is what we call indirect detection. So sometimes if you see some peaks lower and you can see some peaks upper, That is how we modify the eluent to have a different selectivity. Yeah? So in other case, if you are good at maintaining the background, you can actually have negative and positive peaks at the same time. Yeah. So meaning that if you use a medium, like for example, medium conductivity, like this contactless conductivity, yeah? Because if you use weak acid will have a medium conductivity. So the baseline will be in the middle. Yeah. So whatever the cations who has a higher conductivity will go up, and the anions who has a lower conductivity will go down as the negative peaks. So this is how, when we want to use simultaneous determinations of anions and cations at the same time, yeah, using this contactless conductivity. So the same detector is being used for capillary electrophoresis. Yeah. So maybe when I talk about electrophoresis, maybe I will share some of the separations we have before, but right now we don't do any electrophoresis in the lab. Previously, I have one PhD student. He was using electrophoresis to separate drugs. Right now, he's working in the Gifu prefecture. He's in the police department now in the crime lab. Yeah. I think in Indonesia, you also have a crime lab. So yeah, he used capillary electrophoresis. Yeah. So I will share something we have before. What is the problem? When you hear about capillary electrophoresis, it sounds so grand, right? But actually, there are so many problems. Yeah? When you actually do something, it's not so easy to maintain the separation if you're not good. Yeah. So you really need somebody who are experienced to have repeatable results. So when your result is not repeatable, that means whatever you analyze is not reliable. Yeah? You cannot use. Yeah? So for him, because he is working in the crime lab, whatever result he gets from the analysis, sometimes he has to use in a court, yeah, to testify a criminal, you know. So it's it's very serious, yeah, when your result is not reliable. Yeah. So that's why when we make a column or when you use a system, you have to make sure the repeatability, I mean the reproducibility is important. Yeah? If you inject 3 times, same sample, everything the same, but your peaks, your chromatogram is different, that means something is so wrong. Yeah. So in this case, you have to find out what is the problem. And most of the time, you can solve the problem by washing your column, yeah? Because the main thing, the heart, you know, is the column. Yeah? So when the column is contaminated, or sometimes with some absorptions, sometimes you will cause some bad result. So most of the time you can solve by washing the system. You can also wash not only the compounds, you can also wash some small rubbish. Yeah. Sometimes there's some small rubbish inside. You have to wash it. Yeah. Sorry, I hope this if there's any other questions.
Yeah, please, if any participant want to ask Prof. Lim, please, directly or indirectly.
Directly or indirectly. I just saw there's Mora make another good flyer again. Thank you. Anyway, today we mostly talk about the 3 important thing, like the but like I say, whatever it's in our syllabus is the basic. Yeah. So you have to do more reading. Like last week, I think you have the PDF file of the textbook from Gary Christian. So this is the latest version. Yeah, the one I have now is the old version. Yeah, so I use this one for myself, and I still use it now. So this is the old one. I think I used the 4th edition when I was in UKM, University Kebangsaan Malaysia, for my undergraduate. My the lecturer also used Gary Christian's textbook. And in Japan, the Society of the Japan Society for Analytical Chemistry also translate Gary Christian's textbook, and we are recommended to use it in the whole of Japan. Yeah. But because the textbook is so much and is expensive here, so recently we do not want to give the students so much trouble, so we do not force them to use as the textbook, but we just put it recommendation as a reference book. Yeah. So for the textbook, we usually use something simpler, modified by some local professors, Japanese professors. So usually it will involve different kind of the student can also use the textbook for physical chemistry or inorganic chemistry. Yeah. I think in our syllabus here, and Busoja and Moral has give you a list of good reference books. Yeah, the one that by Scotch is also famous. Yeah, so Scotch is also very famous. You can if you have the PDF file or whatever, sometimes it is good to invest in a good book so that you can read. Yeah. I don't know, right now everybody is talking about electronics book, but I still like the traditional book. Yeah? So and I'm still very traditional. So I usually buy a lot of books, and then so sometimes after I don't have time, after buying, I just read and I just look at the photos. I like to look at the photos. So when there's interesting photos, I will, draw myself. So actually how you take notes is quite important. Yeah. So when I came to Japan, in Malaysia, when we take, I don't know, maybe Mora is still young, you don't know because you already have the PDF or the PowerPoint. Yeah. I think maybe Busoja know our generation when we were students. The lecturer used the OHP sheet. Yeah. So OHP is like
I know that.
Really?
Yeah.
Maybe I thought Moral, you're too young to know OHP. Maybe Busoja knows. So I think in our generation, the lecturer will use the OHP and they will write, and then everybody will be busy copy all the notes. Yeah. So, but anyway, how you make your own notes, original notebook is so important. Yeah. Like after coming to Japan, I have a chance to read actually there's one professor in our department, but he already retired. Yeah. So Professor Inagaki, he graduated from Kyoto University, and he was a student, PhD student, together with Professor Fukui Kenichi. So Fukui Kenichi is I think the first Nobel Prize receiver chemistry in quantum chemistry. Yeah. So the paper is written by that PhD student, which is Professor Inagaki, together with Professor Fukui. And after that, Professor Fukui received the Nobel Prize with that paper. So, of course, that Professor Inagaki came to Gifu. Title of the book. Oh, which one? Title of the book. You mean which title? You mean not this one, right? This one is already given by Book 3 last week, I guess. You have the PDF, right? Yeah? Another one is if you look at the your learning details of this program, you have, I think there is a very good program that maybe you can see. Syllabus. Oh, so on. I think you still can see my screen, right? So this one, the separation chemistry course, I think is already distributed to you. So at the last of this page, you can see the references. The last one by Scotch. So this is also one of the most popular book in analytical chemistry, beside G.D. Christian's. Another popular one is we call the Harris, by Harris. So, well, it depends on individual. Yeah, sometimes you might find this better. Sometimes you might find a different one better. So, when I teach analytical chemistry, it's not separation, only analytical chemistry. Actually, I don't use only one textbook. Yeah, I buy 10 textbooks from different professors, from different publishers.
Yeah.
Yes. And then sometimes when I want to look at something, so I will see the same topic from all the books and to see who has the best explanation. Yeah. Then I will use that. Then I will try to use simpler words or whatever, so that the student can understand easier. Yeah? So usually I don't use so much word in my slides because, yeah, I mean, if there's a textbook, the student can read the textbook anytime. So this is one of the textbook in Japanese. It's I think my professor, he already retired, but I keep the books that he wanted to throw away. So next week, if there's a chance, I will take a photo of the books, which my professor, the person who invented capillary liquid chromatography, Professor Takeuchi from Nagoya University. So I will try to take a photos what kind of textbook he was using. Yeah. So maybe you can take a look. Yeah. Oh, I have another question.
Well,
Okay.
Okay, maybe before we close, I have one question, maybe, Prof.
Hi.
Yeah, about Illumine-Induced.
Oh,
Yeah.
okay.
So what the advantage using that method compared to using just cationic or anionic resin?
Yeah, actually, if you can have ionic or anionic resin, the best is to use the original column. Yeah, so the Illumine-Induced only we use when you do not have that column. Yeah. Yeah. So when you do not have an anion exchange or the cation exchange resin for the separations, and in your system you only have the ODS column, but you want to see some anion compounds. So in this case, you will use the Illumine-Induced method so that you can use the same Hplc system, but to separate anions or cations. So that is convenient when you just want to test something with your own system. Yeah? Because Illumine-Induced is just temporary. After you use for the separation, you can use another Illumine to wash away, and then we can return to the original column like a reverse phase. Yeah. Yeah. So that is usually you can use that as a like alternative to your separations.
Okay, thank you, Prof.
Yeah, thank you.
Yeah, and that's it. Yeah, you have finished your explanation.
Yeah, I think so.
Okay, so well, we have come to the end, and again, I would like to say many thanks, yeah, for Professor Lim for an excellent and detailed information, yeah, about size exclusion, about a bit about affinity, and very comprehensive explanation about ion exchange. And I guess this will be delivered again in our webinar in December, right?
In the webinar, I will not talk about the fundamental areas. Maybe I will talk about how we make monoliths column for ion chromatography and the application. Yeah.
Yeah.
So application including the industrial standard. So we call it the JIS. JIS stand for Japan Industrial Standard. There are some methods for testing environmental samples in Japan. Yeah? So maybe usually it might be quite similar all over the world, yeah, because when we have something standards, it will be similar because we are looking at the same kind of compounds that is the contamination. Yeah.
Okay, excellent. And I believe all participants here also can absorb your explanation very well. Yeah. And for all participants, thank you so much for joining this meeting. And we still have another meeting next Tuesday, so don't be forget to join again. And in the last program of visiting lecture of Professor Lim, we will have a webinar. Yeah, you can see the poster in the beginning of our session. Yeah, we collaborate with Indonesian Chemical Society, and we will talk about current application of chromatography. Yeah, so Prof Lim will be co-speaker by Dr. Rafli from IPB. Yeah. So don't forget to register the webinar. I will share the poster in the WhatsApp and in the group. Yeah. So that's it. Thank you for all participation. Thank you so much again for Professor Lim. See you again next week and bye-bye.
Hi, bye-bye.
Thank you, Prof.
Hi, thank you.
Yeah.